This is the third in a set of talks about black hole chemistry, and today we're going to really get into some of the main results that we've obtained over the last, getting on to almost 6 years now for this newly developing subdiscipline. So I want to start off with what came to be called the 4 laws of black hole mechanics, which were constructed in this paper by Bardeen, Carter, and Hawking. It was actually, they did the first 3, and the 4th one came a bit later. So the 0th law is related to what we saw for the law of equilibrium in thermodynamics, that the surface gravity is constant over the event horizon in an equilibrium state. And the second law, or sorry, the first law, that's the 0th, is energy conservation, that if you take differences in mass between nearby solutions, then they're equal to the differences in area times the surface gravity of the black hole, which is assumed the same between each, plus additional work terms, such as the angular velocity times a change in angular momentum between the solutions, the potential times a change in charge between the 2 solutions, and so on. The second law is that the area of the black hole never decreases in any physical process. And then the third law, which came along somewhat later, as Werner Israel formulated it, is that you cannot reduce the surface gravity of the black hole to 0 in any finite number of steps. Now, of course, these laws need to be cast in the context of black hole thermodynamics, and I mentioned last time how that was done. The key element is the surface gravity is identified with temperature, which you can do when you incorporate quantum effects, and the area is identified with 4 times the entropy. So that led to this correspondence. Energy was mass, temperature was surface gravity, entropy was a quarter of the horizon area, and the first law of mechanics on the right was related to the first law of thermodynamics on the left, with the exception of this work term. And black hole chemistry, as it's come to be called, is what happens when you properly incorporate this term on this side of the equation. And that's done like so. The cosmological constant, which Einstein called his biggest blunder, actually can be associated with either a cosmic tension, if lambda is positive, or a cosmic pressure, if lambda is negative, which I pointed out last time. And so what's going on qualitatively in black hole chemistry is it's as though the universe, well, not as though, the universe is filled with a vacuum energy, and larger lambda means the vacuum energy is basically at higher pressure. Now, it's a funny energy because it's negative, rho plus p is 0, but nevertheless, it can be understood that way. So, as I pointed out last time, when you take the possibility that lambda could be considered to be a thermodynamic variable, then you end up getting this modified first law, identifying lambda with pressure. You get a V delta P term, and you find that this integrates up properly to give you this Smar relation in any number of dimensions. And there are no exceptions to this relation being satisfied, some that I have ever found. You will see in the literature sometimes different values of, you won't see this term, and you'll see a similar relation where there's some different coefficient here or something, But in every case I have found where that occurs, it's always because, now I can write on the board, it's always because PV is proportional to TS with some particular coefficient. And when you actually back up and figure out how they got their variables, you discover this relation is satisfied, and when you put in whatever people used here, which they didn't know they were using, you get their modified smart. This follows from Eulerian scaling, as I stated before. So how do you do the chemistry? Well, the way we've done it is to minimize the Gibbs free energy, which is the enthalpy, mass is now enthalpy, minus the heat, Ts. That's the energy left over that you can do work with. Free energy is the energy available by which you can do work, and so physical systems, we assume, minimize that as much as possible. They'd rather waste energy. They'd be lazy, but there's only so much they can waste. Whatever they can't waste, that's what we can do work with. There's an issue, of course, of stability. We don't want just a local minimum. We want a global minimum of the free energy. And we want positivity of the specific heat. And we interpret negative specific heat to generally describe a thermodynamic system that is unstable. Doesn't mean it can't exist, but it's not stable. It's going to become something else. So what we found when we basically take the top equation and apply this criterion, we get what we called everyday black hole thermodynamics, or black hole chemistry. And what I want to talk about now is how these different phenomena are understood in this context. The first one is well known. It's the Hawking-Page transition. It was found over 30 years ago by Hawking and Page, and it was the first known phase transition of a black hole. But we found quite a number of others. These are the next ones. The Vanderwaal's fluid phase transition was found about 5 years ago, or 6 years ago, by David Kuznak and me. And then we've discovered some other phenomena that actually we didn't know what they were at first, but as we did some digging in the literature, we discovered these had been seen a long time ago in the context of chemistry, reentrant phase transitions, and, well, this is something you learn in high school, the triple point of water, and we discovered black holes can have triple points just like water has a triple point where solid, liquid, and gas, the three phases of water, all are indistinguishable at a particular value of pressure and temperature. So let's look at the Hawking-Page transition. So you can, they did it for a 3+1 dimensional black hole, but you can do it for a, any dimensional black hole. So there's the metric. And what they did was compute the free energy of the black hole using slightly different methods than what I've presented before, but you basically get the same answer. And what they found was this. If you plot the free energy of the black hole as a function of temperature, you find you get two branches. You get a red one here and a blue one there. And you march along these branches by raising the size of the black hole. So if you start with a small black hole, you find the free energy is here. And it gets bigger and bigger and bigger until it reaches a maximal cusp, in which case it turns around and goes this way. So it's clear, and this just goes, it's very steep, but this just goes on and on forever. So it's pretty clear that if you're here, the global minimum is actually there, and you'd rather be a large black hole. But then they noticed, of course, something else. They found that the free energy goes negative at a particular temperature, which has come to be called the Hawking-Page temperature, or you could just call it a critical temperature. And the way to think of, you can think about it like this. Suppose you start with a large black hole in ADS. This black hole will want to radiate. As it radiates, it'll get smaller and smaller, and it will march this way. It's the stable minimum, but eventually it will be such that its free energy goes to zero. At which point, they argued, it would be thermodynamically favorable for the black hole to disappear entirely and become pure radiation. Perhaps a gas of thermal gravitons in ADS. Now, my personal view is there's a bit of a problem with that concept because pure ADS has no radiation in it at all. So thermal ADS is not really just ADS, but nevertheless, the idea would be that a black hole that is smaller, such that its temperature is a bit colder, it's unstable, and thermodynamically it'll go poof and become radiation. That value of K is +1, 0, or -1 for hyperbolic black holes. So what happens is anti-de Sitter space is kind of like a confining box for gravity. If you throw a rock in anti-de Sitter space, no matter what initial velocity you give it, eventually it will come back to you, because no massive particle can ever escape to infinity in ADS. If you shine a flashlight, eventually the light will get to infinity, but any massive particle will come back to you. So in that sense, it's kind of like a confining box. So as the black hole radiates, it's filling up ADS with heat, but the gravity of the heat is kind of trapped in the ADS space, and so you can get the black hole to be in thermal equilibrium with its own heat, and if it's cold enough, eventually it would rather just be all radiation. So that's perhaps another way of looking at it. So this is a first order transition. What that means is the free energy is continuous, but its derivative is clearly discontinuous at this point. So you're going along a smooth curve, and then all of a sudden, you point that way. And that's a hallmark in thermodynamics of a first order phase transition. Okay, so the minimal length, or the minimal temperature the black hole can have is given by 1 over the ADS length, where lambda, I guess I didn't write it on the slide, but I'll write it here. Lambda is d minus 2, d minus 1 divided by 2L squared. So that L is called the ADS length. And the specific heat of the large hole is positive. The specific heat of the small hole is negative. Not surprisingly, this is higher than what that would be down there. Okay, so here's an expression for the temperature explicitly in d dimensions. And it was pointed out after the ADS-CFT correspondence conjecture was formulated. Witten suggested that this correspondence implied that the Hawking-Page phase transition is a phase transition in a dual CFT to a quark-gluon plasma from a set of quark-bound states. What David and I pointed out a bit later than the first thing we did in black hole chemistry, but not a lot later, that the fluid interpretation of this is like, curiously enough, a solid-liquid transition, where the large black hole is like a liquid, it's warmer, the radiation is more like a solid. Now, that sounds a bit strange, radiation isn't really a solid, but it's like it in the sense that there's an infinite line of coexistence between the pressure, remember, pressure is like 1 over the length squared, and the temperature, and the length is variable. So what you find is that there is no end to that coexistence line, very much like a solid and liquid in many systems in the real world. If a system is hot enough, at any pressure it'll always be a liquid. Conversely, if it's cold enough, you can put enough pressure on it to crush it into a solid. So it's a phase transition kind of like that. It has an infinite coexistence line. the equation of state, if you write L squared is equal to 1 over L squared, is equal to 8 pi pressure over 3. If you put that in there, and there's a relationship between R plus and the specific volume that I'll spell out explicitly in a few minutes, then you find that you get this equation of state. Pressure volume is temperature minus this thing here. So let's suppose we had planar topology. K was 0. That's a black hole. Instead of being like a sphere, it's like a plane. Or a torus if you identify it. You get 0, and then you get what I first learned about thermodynamics in high school. PV is nRT. Everybody remember that? Right? And the nR has been set to unity by choosing units, but that's the ideal gas equation. A planar black hole is like an ideal gas. A spherical black hole or a hyperbolic black hole has contributions to the equation of state that either are negative or positive, inversely like the volume, depending on which one that you get, and that's going to matter a lot later. This specific volume is related to the horizon length by this equation here, where this is the Planck length squared. And you can actually show that, apart from this factor of 6, that that's the thermodynamic volume of the black hole divided by the number of degrees of freedom, where if you believe that entropy is a real thing for a black hole, then the horizon area has a certain number of degrees of freedom, and so the number of degrees of freedom has to be proportional to the horizon area in units of Planck length. So basically, if you put this into this, you get this equation. So V is what you would call in thermodynamics the specific volume of the system. And it's more useful to write equations that way, so I'm going to be doing that a lot here. But I'll try to remind you what happens from time to time as I do this. So any questions about this? This is the simplest kind of black hole chemistry.
So I guess that when K is 0, also the graph, pressure versus temperature will change.
Yeah, that's right. This is for K equals 1, that graph. This is for K equals 1.
And then you have to consider the ADS soliton, no? At least for phase transitions.
That's later. If I never heard of an ADS salt, well, the ADS salt, yeah, the planar, you're right. That's different. Yeah, you're right. Okay, so Vanderwaal's fluids. This is where the subject began to get interesting, so I'm going to give you a review of the Vanderwaal's fluid. How many have encountered this somewhere in their past scientific education? Vanderwaal's fluid, yeah? Familiar? Okay, so it's going to be a review. So Vanderwaal's equation can actually be written like so. I should have put the original up. But it's a generalization of PV as nRT, where the quantity B takes, I don't have a pointer here, the quantity B takes account, oh, I guess I can do this. The quantity B takes account of the fact that if you had a gas, the molecules are of finite size, and so you can't crush the gas to 0 volume. And A takes account in a crude way of the fact that the gas molecules can attract each other or interact with each other. So if you rewrite the standard Vanderwaal's equation out, this is what you get. And you can find its critical point by asking where, if you look at pressure as a function of volume, where does it have a point of inflection? Where do the first and second derivatives vanish? And if you do that, then you get what we call the critical values for the temperature, volume, specific volume in this case, and pressure. And so if you rescale these variables in terms of their critical values, you obtain what is called the law of corresponding states, which is just a way of rewriting the Vanderwaal's equation to put temperature in units of critical temperature on one side and these other variables on the other side. So this is, sorry?
Why the second derivative has to be 0?
When? Sorry.
Why does?
Well, that's the definition of criticality. This defines a critical point when both of these are 0. And all I'm saying is the reason for doing this, we're going to look at this a lot as this goes on, but all I'm saying here is that if I wanted to rewrite this equation in terms of the critical values, this is how I would do it. If you compute that, this is what you get. If you then rescale, this is what you get for Vanderwaal. So the law of corresponding states is a different way of writing Vanderwaal's equation.
Typically, you said that you have a second order phase transition?
When you're at that temperature, yeah, that's right. You'll have a second order phase transition when that happens. Now, for a Vanderwaal's fluid, there's a ratio between these quantities that you might be able to compute with your eye, but if you can't, you find it's this. If you take PV and divide by KT, you get 3/8. And the diagram here, gets, I think, to what Andres was mentioning earlier. The PV diagram for a Vanderwaal's fluid this would be the minimal temperature of the system. If you go below that, you get negative pressure. So let's not worry about that. The point is that if you're below the critical temperature, you have a minimum and you have a maximum. If you're above the critical temperature, you have no min or max at all. So what does this mean? If I have a box of gas, it's at a big volume, I'm going to start squeezing it. If I'm above critical temperature, I can never tell the difference between a gas and a liquid. I can keep squeezing and squeezing and squeezing, and I find the pressure smoothly goes up. But if I'm below the critical temperature, I will reach a point given by Maxwell's equal area law that I'll mention in a minute. I'll reach a point at where this gas at that particular temperature is so compressed that the molecules start condensing into liquid. And as I squeeze it more, I get more and more liquid. The pressure doesn't go up, because every time the gas pressure would go up, the molecules will condense to liquid. Eventually, the whole thing is liquid, and then it's really hard to compress it, and every time I do, the pressure goes way up, because we all know liquids exert a lot more pressure than gases. So that would be, actually, does this shine at all? Just occurred to me this might have a pointer. And the answer is, if it does, it's not working. Okay. So, let's see if you can get it working. So that's what this is. How do I know where the transition occurs? Well, Maxwell figured out and told us that it occurs wherever you draw a line on a given curve such that the upper area and the lower area are the same. And that's given by this equation right here. It's basically the amount of work you do on the liquid side is the same as the amount of work you do on the gas side. The work balances. And so what actually happens, oh, that's nice. So how do I do it? Oh, I love this. It's so nice. Oh, where's the, all right, that's a bit, okay, this is fun, except now I don't want it all the time.
You have to press pointer to get rid of it.
Okay, all right.
This is more standard.
That would be better, yeah, that's a little faster. Okay, so in other words, you see how much fun this is? So you slide up here, then you go along this line, and then you go way up there. Of course, if you're above criticality, you just go here. And at criticality, you have a second order phase transition, which is the edge at which gas and liquid just become indistinguishable from one.
Do you want to change it with the pointer? You need to do this.
Oh, boy, that's cool. Okay. Let's see if this works. And it does. Oh, bingo. Thank you so much, sir. So, the Gibbs free energy. Let's look at that. What we were looking at before was the equation of state. Well, it turns out for a Vanderwaal's fluid, you can explicitly calculate the Gibbs free energy. And it has this expression as a function of temperature given by this logarithm of V minus V times T to 3 halves divided by some constant that's characteristic of the gas minus these two terms here with the kT in front. And if you plot this function, G is a function of pressure and temperature for a fixed volume, you get this rather strange structure here that has this swallowtail. And it's rather hard to see it, but if you imagine taking slices this way along P, if I slice for a large P, 0.04, it's not that large, but it's large, then I'm on the smooth branch, which is this branch way out here. But then I reach a point where I hit this cusp, which is this point right there. That's the critical pressure, below which we're now going to have phase transitions. And then you get what are called in the literature swallowtails, these triangle-like structures. They look like the tails of a swallow bird, you know, flat, so they call them swallowtails. Some people write them as swallow space tail, but you're not swallowing a tail, right? It's a bird, but it's a swallowtail. So these get bigger and bigger as you lower the pressure. So if you remember the Hawking-Page transition, for example, or anything in thermodynamics, if I started out with a hot system and I was at low pressure, as I cooled the system down, I would go up this curve, but when I hit that point, I would then move this way. And that would be a first-order phase transition from gas to liquid. And that's how you can interpret this diagram. Okay, is that any questions about that?
What about a question? What about the slopes in the GT plot? Is the slope is the negative of the entropy, right?
Yeah.
So,
in this case, it would be dGB. That's why I've got the first law here.
Okay.
That's right. dG is negative S. If you rewrite, if you take dG and expand it out and simplify with the first law, this is what you get. dG is minus entropy dt plus volume d pressure. That's right.
so there are parts in the plot where the entropy is negative, right?
No, there are parts in the plot where there's instability in specific heat. You take the next derivative and it's negative.
But what about...
Oops, what did I do now? Microsoft, don't send them anything. Okay, sorry about this. There's some of these and I exited the program. Okay, sorry, there was there was a question, sorry.
So what about the... Because you see when the slope goes from left to right,
Yeah.
is minus S is positive, right?
Yeah. Oh, I see, yeah, you're saying the slope is the wrong sign there. So I think eventually eventually you do reach a point of instability. That's a good question, because ultimately, what's being plotted here is that function. I will have to think about that. You get it positive for small values, right? It goes negative, and eventually it's all the way there. So I think there's a point of instability here that you can't make use of. But there is a small swallowtail region around here. Okay, the critical exponents, we're going to be seeing them a number of times, so I'm just going to tell you what they are. The specific heat is T ds dt at constant volume, and near criticality, if you remember, tau is temperature over critical temperature. In general, you find you can write this as tau minus 1 to some exponent negative alpha. The specific heat diverges at criticality, and it diverges like some power of T minus T critical, and we call that power alpha. The order parameter is the difference between the volumes of the gas and the liquid at criticality, and it likewise is some power of T minus T critical, and we call that power beta. And that will depend on what the substance is. So when tau is 1, the volumes are the same. When you're close to 1, they're slightly different. The isothermal compressibility is given by dV dP over V with a negative sign, and that critical exponent is gamma. And the critical isotherm is V minus Vc to the exponent delta. So as the pressure approaches criticality, the volume approaches it, but at a different rate that is given by volume approaches its critical value, but a different rate given by delta. Now for a Vanderwaals fluid, this is what you get. Alpha is 0, beta is a half. So alpha 0 means it's actually not diverging. Beta is a half, gamma is 1, and delta is 3. And these also happen to be the values from mean field theory. These values occur most commonly in thermodynamic systems. They're not true for every system, but they're true for many systems. The line of coexistence is found by this Clausius-Clapeyron equation, which is the difference between the entropy of the gas and liquid divided by the difference in volumes as you, well, not just at criticality, for anything. So you can use this equation to find where this line occurs, demanding it's equal on both sides, and when you hit the critical point, then you don't have this line anymore. So, now let's look at charged ADS black holes. And what we learned is they could be understood as Vanderwaals fluids, and that's in this paper here. So here is the spherically symmetric metric for anti de Sitter space, where V is given by this function where you now have the charge term and you have a charge potential. It's easy to compute the temperature and the entropy and the pressure. The entropy is a quarter of the area. The temperature is the first derivative of V evaluated where V is 0. The electric potential is Q divided by R plus. R plus is the horizon radius. The pressure, by definition, is negative lambda over 8 pi, or 3 over 8 pi L squared. And the volume, as I showed you last time, is the Euclidean volume of the black hole, for 4/3 pi R plus Q. So, you can easily show that the Spar relation and the first law are satisfied by these values. It's arithmetic. Okay, well, so what? Well, David and I thought, let's look at this and see what happens. And in particular, what you do is you use this equation to get rid of L squared in terms of pressure, use this equation to get rid of R plus in terms of volume, and you find the equation of state. And this is how it's done. Here's the equation for temperature and pressure. So we rewrite this to get pressure as a function of temperature and R plus. And then it was clear that R plus was related to the volume, but it wasn't quite obvious how to connect these two. So one way of doing it is to ask, well, these are all in geometric units. G is 1, H bar is 1, C is 1. In the real world, the right units for pressure are given by H bar C over the Planck length squared times this geometric P. This has units of force per area. And in the real world, temperature is H bar C over Boltzmann's constant times this geometric temperature. So we put this in here, and we figured, if you just put these in here, then you get real world pressure is equal to KB real world temperature over this. And so it's for this reason that we called this thing little v, and then we found that this quantity is actually the thermodynamics specific volume, the full volume divided by the number of degrees of freedom. So, here is our equation of state. Notice if these terms weren't there, you get good old PV equals nRT. Now, this equation of state has Vanderwaals behavior. Why? Because at large V, it falls off like 1 over V. At small v, it's growing like v to the 4th. But at intermediate v, it's going to turn around because of this minus sign. This is for a spherical black hole. So, if you look at the Gibbs free energy at fixed charge, this is what it looks like. Here is this funny swallowtail structure. It's not exactly the same as for a Vanderwaals fluid, but it's qualitatively similar. A smooth part for large pressure and a swallowtail part for small pressure. And when you plot it, you get this structure that's very similar to a Vanderwaals fluid. You find that large black holes have a very steep growth in G. It smoothly goes over above critical pressure. Below critical pressure, you get a swallowtail, so you will get a first-order phase transition. That's large, and that's small. So you would go up this branch here, you'd have a first-order transition, and then the big charged black hole, as it radiates, would suddenly want to shrink a lot to become a small charged black hole. It will not become thermal radiation, because thermal radiation is electrically neutral, and we have fixed the charge. So you don't get a Hawking page transition here. Now, we were not the first people to suggest there might be some analogy. It was actually Andrew Chandler and collaborators did in the late 90s. But they didn't have a pressure-volume term. And what we pointed out, which we weren't attacked for, but we thought we might be, is basically they were wrong. They had the right idea, but they implemented it wrong. There were two ways you could do it. One was by this comparison, that for the ADS black hole, its charge in fluid language should be the temperature. Its pressure, its temperature, or rather inverse temperature in ADS language, would be fluid pressure, and R plus would still be the volume. The other way of doing it is that the inverse temperature for the black hole was the fluid temperature, the charge could be interpreted as the pressure, and the electromagnetic potential would be the volume. They actually looked at both. If you fix the electrostatic potential, this is generally called the grand canonical ensemble. So that's hence this name instead of this name, whereas you fix the charge, it's canonical. Well, we analyzed these, and neither of them work. First of all, you've got a confusion between intensive and extensive quantities, right here, for example.
Sorry, I don't understand.
This is extensive, this is intensive, yes.
Why the pressure is 1 over the temperature?
Because they wanted to get an analogy with Vanderwaal's fluid, and they didn't have an explicit pressure term. They had no idea of the VDP. So they noticed that if you plotted free energy, they did it for, I'm trying to remember, they did it for Q versus inverse temperature, and they got a swallowtail, so they made these guesses. In black hole chemistry, you get a complete analogy. The black hole temperature is the fluid temperature. The pressure is the fluid pressure. The volume is the volume. Yeah.
Inside the energy momentum of the black hole, there is an energy density and also pressure term. Can we use this pressure term equal to this pressure?
Sorry, I didn't hear the first part. The what did you say?
In the Einstein equation,
Yes.
on the right side there is the energy momentum tensor, and inside there are pressure terms.
Oh, you mean from the electromagnetic field?
Yeah. So,
Well, an electromagnetic field isn't directly interpretable as a perfect fluid, so we don't do that. We interpret lambda that way, but not the other stuff. There is an approach, which I have looked at in a few papers, and which I was not planning to talk about here, though maybe if I get enough time between now and tomorrow, I could add it in, but I probably won't. There's an approach called horizon thermodynamics, in which you actually do what you're saying. And so the pressure is not just lambda, it's given by contributions from other things, and there's a way of doing that. Padmanabhan advocated this approach a number of years ago. I'm not very keen on it, because you get a lot of confusion again, much worse than this, between different thermodynamic variables. So we don't do that. Here, this is pressure, and anything else is some other work term. Yeah?
I may be anticipating to some results that you may present later, but I'm confused somehow with the thermodynamic volume.
Yes.
Because in the sense of entropy, for instance, get corrected in Einstein-Gauss-Bonnet, for instance.
Yes.
So the entropy gets corrected is no longer the area.
Yeah. You'll see that come up later here.
In the volume, you get a correction with.
You can. It depends on the black hole. That's right.
Because I'm thinking that is very natural the volume, because in Einstein-Hilbert the action is proportional to the volume. So if you sort of renormalize the volume, you will get the volume of the black hole. But in Einstein-Gauss-Bonnet it's not longer the case.
Well, you're right, but I don't know if you were here yesterday, but the volume is not always the Euclidean volume of the black hole, even in Einstein gravity. It happens to be true for this particular class of black holes, but in general it is not that. So volume is by definition, volume is that which is conjugate to pressure. What it ultimately means in degrees of freedom has yet to be understood. I'm going to mention that at the very end of these things.
So is there any connection? Are you familiar with the, it's more in the context of mathematics, what they call Anderson theorem?
What they call?
Anderson theorem. It's something related to renormalized volume in asymptotically ADS, hyperbolic spacetimes.
I've heard of it, but I haven't used it much. We haven't used it here. Okay. So, what about the critical behavior of this thing? Well, this is the definition of criticality. So you take these derivatives of this equation. This is what you get in terms of charge. The charge should be thought of here as a control parameter, a knob I can turn. I'm going to say I'm going to look at black holes with this much charge, I'm going to look at with this other charge, see what they do. So these are given in terms of this control parameter, and curiously enough, you get 3/8, just like a Vanderwaal's fluid. In terms, if you rescale things in terms of criticality, this is what the law of corresponding, where the G should be here, states looks like. Not exactly the same as a Vanderwaal's fluid, qualitatively similar. And here's the pressure volume diagram. You get you get qualitatively the same thing as for an actual Vanderwaal's fluid. Yeah.
For dynamic black hole, is everything the same?
For what?
Dynamic black hole with magnetic charge?
That I do not know because we haven't looked at that. In a simple sense, the answer is yes. The reason why I'm hesitating is you've got to worry a little bit about fixing both electric and magnetic charge. So that case probably bears, somebody might have looked at it already. There's lots and lots and lots of papers on this subject. Here is the law of corresponding states. Here's the small black hole, large black hole transition. There's the critical point, just like the normal liquid gas. Small black holes are like liquid, large black holes are like gas. That always feels backwards to me, but nevertheless, that's the way it is. How would you understand this? Well, suppose I were an ADS and I had lots of big black holes that were far away from each other. The Einstein equations aren't solved exactly, but approximately around each one. Then, if I were able to crank up the, or rather either cool the system down by some divine powers, then I would find that slowly the large guys, one would be small, then this guy small, then this guy small, small. And that would be like the liquid-gas transition until eventually everything in the system were a small black hole. How do I understand gas-liquid? Well, I got a gas, and then a little clump condenses to a drop of water, and another to a drop of water, and another drop, and another drop, and another drop, until the whole thing's water. It's not any different.
Again, if you, but then these small black holes are unstable, right?
Well, no, they're not once once they're cold enough. They're not because they're charged.
Well,
They're not unstable along that branch. They are unstable when it's hot enough, but they're not unstable when it's cold. The large ones are unstable when it's cold. In the Hawking-Page thing, big black holes would rather go poof to radiation, but when they have charge, they can't. They've got to conserve their charge, so they go. It's like a gas is condensing to a liquid. It's just like that.
The small black holes are stable when they have electric charge.
Yes. First, when they're cold enough. When they're cold enough.
Okay.
Yeah. If you compute the critical exponents, it's just like a Vanderwaals fluid or what you get from mean field theory. Now, so then we thought, well, this is kind of neat. Let's look at higher dimensions. Will we get something different? Well, here, then the analogy is weaker because Charnel Laguna-Seca and David and I worked this out here. In d dimensions with n particles, if you take the Hamiltonian non-relativistically and compute the partition function, you can use this to get Vanderwaal's equation, and the short story is you get exactly what you get in 3 spatial dimensions. Vanderwaal's equation, to my surprise, is insensitive to the number of dimensions. It doesn't care, at least 3 and up. It doesn't care. And this argument, I'm not going to go through all the arithmetic in detail, but basically the pressure is minus dF dV. When you compute it from the free energy F, you get this equation here. So once we go to higher dimensions, we're going to get Vanderwaal's like behavior, but we're going to go farther away from the specifics of this equation because it's insensitive to the number of dimensions. So for the d-dimensional ADS black holes, the metric is the same, except you have d-2 spherical volume element. Here I have written the metric function, potential, and mass and charge that are measured at infinity in terms of little m and little q. Here's all the thermodynamic parameters. You can calculate them all out. Now you see their explicit dimensional dependence. You've still got kind of a spherical, well, you actually do. This is the volume of a sphere in d-1 dimensions. And you can show the first law and SMAR are satisfied by these quantities. The object of the game is to ask if anything different happens, and the answer is not really. A little bit different happens. The equation of state now has this d-dimensional dependence, but notice you've got a positive 1 over volume, a negative 1 over volume squared, and then a charge over volume to some power occurring. So the physical equation of state in terms of this specific volume, notice it's still proportional to R plus, becomes this. 1 over volume minus 1 over volume squared plus q squared over volume to the 2d minus 4. So this decreases faster, but it's got a positive sign, so for small volume it's just going to shoot up faster. And so what you end up finding is that in 4 dimensions or 10, you get the same kind of swallowtails. It's just that because of that extra power of 1 over v to the 2d minus 4, these swallowtails, as dimension increases, just go up sharper, but they're still swallowtails. They're just big swallowtails. You got big swallows in higher dimensions, I guess.
And now it's better, right? Because if you don't have this positive slope.
You never have the thing flipping over from black hole. Yeah.
Is it possible to do this thing for not black hole, but for the universe? For example, our universe is make a fast transition to another universe.
Well, that's wait till tomorrow. The answer is partly we don't fully know yet. In principle, I would say why not, but you need to think carefully through the thermodynamic concepts. So what you're saying is a frontier area. What about the critical behavior? Well, now you find that instead of 3/8, you get this factor. If you put d equals 4, you get 8 minus 5 is 3 over 16 minus 8 is 8. And so this is the generalization of the 3/8 to higher dimensions. This is the law of corresponding states. I've got to fix that. And here are the PV diagrams in 4 dimensions and 10. So you get the same kind of qualitative behavior. The difference is that the max-min get crushed a bit closer together, but you still will have a first-order phase transition, a critical temperature, and then you'll have the smooth thing. So, here are, if you want to see all the dimensions together for where the phases are different to criticality, if you plot pressure versus temperature, the critical point increases with increasing number. 10 is way up off here. I couldn't draw it, but there is a critical point for 10. It's just up in the ceiling somewhere. Okay, so the critical point grows with increasing dimensionality. It's at a higher pressure and temperature, but it is there for any dimension. Oh, and in any dimension, this is always true. These are dimensionally independent for a charged black hole. All right, well now let's do something more complicated. Kerr-Newman black hole. So this is what I wrote down before in 4 dimensions. This is the charged Kerr solution, where the charged Kerr ADS solution, which was found by Brandon Carter, 1970 sometime. And so the metric function looks like this. A is the rotation parameter, Q is the charge parameter, and this is what the thermodynamic variables look like. They care about this function chi, which is 1 minus a squared over L squared, and these solutions make sense only when A is less than L. When A approaches L, you have what is called an ultra-spinning black hole, and you have to rescale parameters. So I'm not going to do that here for now. Okay? So notice the volume is no longer the spherical volume. It gets corrected by this factor here. But, so now, what about the equation of state? Well, this is now painful. What I would do is I would take this equation where I've put in the chi-squared and I've removed L and I've written L in terms of pressure. Well, this is a quartic equation for A in terms of J. You could solve it, but if you've ever solved a quartic, it's a mess. But you could do it, and then what you would have to do is put that solution for the quartic into here, and then try to solve for the pressure in terms of temperature, volume, and charge, and you can't do that analytically. Then you get stuck, because you have to invert all these 4th roots. It's not doable. So you have to do this numerically. You can expand in power if you want. You don't have to. You can expand in powers of J, and this is what you get. So the leading term, remember J is small, the leading term is what we got for the Reissner-Nordstrom case. Here's the first order corrections for J, up to J order J squared. So you can see it's much messier. But that doesn't mean it isn't doable. You just do it using a computer. And here's the quantities again. And what you find is we once again get a first order phase transition from large to small. So that was a bit disappointing. For 4 dimensions, we, did not see anything different. So you still have a critical value. Now if you turn off the charge, which is what's done here, I didn't say it, now you find instead of 3/8 for a rotating black hole with no charge, you get a first order transition, but the critical ratio is 5/12 instead of 3/8. Qualitatively the same, quantitatively not the same. So then we began to discover interesting things, because we did this,
What happened with the extremal cases? Do you have any...
They have 0 temperature. So the extremal case is right there. 0 pressure, 0 temperature.
But the pressure is constant?
This is given by where the phase diagram is there. So 0 pressure is 0 lambda.
But that's funny.
So...
Because you can have 0 temperature with 5 lambda.
So the answer is you have to analyze that separately. We have not done that. Okay.
So a question before you go there. So you work rather on a case-by-case basis. I mean, in general, thermodynamics relations are sort of identities that one can prove for a very general sort of solution. As long as you have a time-like Killing vector, rotational Killing vector, you can prove based on just geometric identities, very generic thermodynamic relations. Here in this case, no one had been able to find such a thing.
And I don't believe you can, because what I hope to demonstrate by implication here is there are lots of kinds of black holes, the way there are lots of thermodynamic systems. My T is a thermodynamic system. A polymer is a different thermodynamic system. A plasma is yet another, and you can't, I mean, you get some common behavior, but in some sense you do have to do it case by case. I'm not going to learn by studying the thermodynamics of a plasma what the thermodynamic behavior is of a polymer. I would be a stock. I'll find some common features, but the underlying microscopics is very different. So, anyway, we found something different, and this is where the subject began, I think, to get a lot more interesting. And that was the notion of a re-entrant phase transition. At first, we didn't know what this was, and then we discovered this is what it was, and we discovered that it was actually first observed in 1904 by a guy named Hudson. What does it mean? If you take a thermodynamic system and you monotonically increase or decrease one parameter, and you go from one phase to another, and then back to the first, or perhaps to a different phase, that is a, well, re-entrant means you go back to the first. That's a re-entrant phase transition. And Hudson found it by looking at nicotine and water in 1904, and this is a diagram from his original paper. He took nicotine as a liquid, water as a liquid, he put them together. And he discovered that, so here's the percentage of nicotine and here's the temperature. So if you had the right percentage of nicotine, somewhere in this range, when the nicotine and water mixture was cold, they were fully mixed together. When you warm them up, they separate into one phase. One of them has water on top, the other has nicotine on top. It is nicotine on top, water on top. But as it gets really hot, it's all fully mixed again. That is a re-entrant phase transition, mixed to separate to mixed. Why is that? Well, when it's hot, it's easy to understand. The molecules are moving so fast that the water and nicotine molecules just go right through each other. It's just a big mess. It's mixed when it's cold because the water molecules polar bond to the nicotine, and so it becomes one substance. But in between, generally these molecules don't like each other. They repel, and so they separate. Now, this is...
It's funny when also when you have also this division to the right and to the left.
Yes, and when you have a very high percentage of nicotine or a very low percentage, there isn't enough to get a good separation between the two.
It's just that you cannot observe it.
Well, to my knowledge, you don't get it because I think the water tends to keep polar bonding to itself on either side. This has been seen in lots of places, and there's physics reports about it if you're interested, in gels, in ferroelectrics, in liquid crystals, in binary gases, in many component fluids. This is seen all over the place, but never in black holes until now. Well, a few years ago. If you take a singly rotating black hole but put it in higher dimensions, so a higher dimensional rotating black hole, but there's just one rotation axis, you could have more in higher dimensions. Here's the parameters. This is an exact solution to Einstein equations. Here are the thermodynamic mass, J, angular velocity at the horizon, temperature, entropy, in d dimensions for this particular object. SMAR and first law are satisfied, just to show you I'm really not cheating. You find, well, at first we thought, well, 5D, nothing different happens. swallowtail, first order, large, small transition. But when we went beyond 5 and looked carefully, we found something strange. Here's the large pressure behavior. You get a cusp, not a swallowtail. It ends here. There's no black hole. You get a kink at criticality. But there's a region in which the swallowtail doesn't go all the way over here. It stops. And that is what we call first a 0th order phase transition. Let's zoom in on that. This is for a particular range of pressures. If you believe in minimality of the Gibbs free energy, start out hot. You've got a large black hole, a first order to a small, but then the small can't exist. It goes back the other way into instability. The stable solution is here, a large black hole. Large, small, and you jump to large. We call this 0th order because the Gibbs free energy is discontinuous here. There's latent heat, if you like. And this is what Hudson saw in 1904. Large, small, large. Now, it doesn't happen everywhere. You have to have a particular range of pressures. But nevertheless, it does happen. It's not a wide range, but it does happen. Well, Hudson, same thing. He couldn't have all percentages of nicotine. He only had some of them that worked. So it really is very much like what he saw. To address an objection people have made to black hole chemistry, I can't vary lambda. If you don't like varying lambda, you don't need to. Because if you fix a constant pressure in this range, you're going to see this. There will be a fixed value of lambda that will give you a reentrant phase transition. In fact, there's a range of fixed values. Black hole chemistry doesn't require a fixed lambda to get its, a variable lambda to get its phenomenon. The phenomenon are easily found by varying lambda. But you don't have to have it if you don't want to.
Just a question. I didn't see the discontinuity in G.
It's very small, right? Right here you end, and this vertical line shows you at this temperature, if you make it any colder, you've got to jump back to that branch.
Okay.
The hole is big, it shrinks to small, and then boom, it wants to be big again. Here is what it looks like on the pressure versus temperature diagram. This is this coexistence line with the critical point. This tiny region zoomed in here is the reentrant thing. Large, small, we call it intermediate because these black holes are smaller than those, but qualitatively they're big. Quantitatively they're not as big. So there it is again, and here's the analogy. Mixed is like intermediate, separate is like small, mixed is like large. And there is, one other thing, there is a region, I can't go there forever. In this region, for these values of pressure, or lambda, and these temperatures, there's no black hole solution that exists. So you can't go all the way here, but this region certainly has reentrance, yeah.
So you said that this happens for the D bigger than 5, and what happens, so this doesn't happen at all for D equals 4, right?
It has not happened for rotating in D equals 4 or D equals 5, but in 6 and up it does. The dimensionality does matter here. That's again to this universal question. You can't do it. If you try, you'll fail. Unless there may be some super duper ultimate theory that cranks the dimension and you see everything, but we don't have that yet. We've got to go from the bottom up. I don't even know if it'll ever be possible to go from the top down. It would be like saying I'm ultimately going to have a theory of molecules that unifies polymers with plasmas, with liquids, with, maybe, but I'm pretty skeptical. I think condensed matter physicists are going to be in business for a long time. Okay, you can take different, remember the equation of state cannot be explicitly computed, but you can take large J and small j limits. I showed you the small j limit. That's this. Here's the large limit, or the ultra-spinning limit, when A is very close to M. And you see that the numerical curves given by the crosses match these very well. Large volume, it turns out the slow curves, the red curves are the slow ones, and they match the equation of state out at large volumes. This blue curve here goes very steeply. It matches the equation of state way down here, way down here. The intermediate stuff that shows you you've got a phase transition you cannot get from either limit. So here we've got a max, we've got a maximum, a minimum, and then goes up again, and then eventually it's unstable. And here's it easy, max, min, and then it's unstable. But you have an equal area law in this zone. But you cannot approximate that. At least we haven't found any way to do it. You can actually see a reentrant phase transition if you look at, instead of pressure versus temperature, angular momentum versus temperature, and here it is again, large to small to large. And as I emphasized before, this is a paper in Natasha, David, and Zainab Shirkantamad. They don't require a variable lambda. Just the way that you wouldn't have to vary j. I could say just fix a j right here. You're going to see this transition. Big, small, big. It occurs in any d, this is Andre's question, greater than 6. It may be because you could get black hole to black brane transitions there, and we think this might be connected with that, but we're still not sure. Okay, can I go to triple points? Triple points are what happen when you get two swallowtails that merge together at the same place. This happens in the real world, solid, liquid, gas for water. So here is, this is a black hole. I didn't write it down, and some may not know, but if you go to more than 4 dimensions, you have more than one possible rotation plane. And this is the way you need to think about it. Normally, when we teach rotation, we imagine rotating about some axis. But the right way to think about it, if you want to live in higher dimensional land, is a rotational plane. So here's a plane, and I have something rotating in this plane. If I have more than 4 dimensions, more than 3 spatial dimensions, I can have a plane in, suppose my dimensions are w, x, y, and z. Well, here is the xy plane, but I can have a wz plane that also has a rotation. And this plane in the higher dimensional world is orthogonal to that one. I can't draw more than 3 space dimensions, but mathematically you can get both. And that means you can have black holes in higher dimensions in general have more than one rotation. You can have 2 rotation parameters. So we looked at that in 6 dimensions, and others, but in 6 you can get it. And we found that for a certain ratio of the 2 angular momenta, say that one, there was a range of pressures where you got 2 swallowtails that merged together. So here's the free energy versus temperature. Here you're above actually you're at first critical temperature. Above criticality it's smooth. Then you get the kink at criticality. Then you get 1 swallowtail. But once you're below a second critical value, you get another swallowtail, a very narrow, sharp one, going up to this swallowtail and over. And then you find that right here, you've got both swallow. This guy grows really fast, this guy moves in here, and they overlap where their first order phase transitions are the same, and that's what we call a triple point. So here it is, and if you zoom in on that, in this range between P critical 1, P critical 2, you've got a triple point right there where you've got this line of coexistence ending in critical point 2. The other swallowtail gives you this line of coexistence ending in critical 1. You got a small black hole here, a large one here. They're indistinguishable up there. but here you've got yet another kind of black hole in between. These are indistinguishable, but right here you've got a small, intermediate, and large, distinguishable, all indistinguishable right there, just like water. Just like water. Gas, liquid, solid. The only difference is for water, this just goes on indefinitely. For the black holes, it doesn't. But that doesn't matter to see this behavior. So again, it's complicated. We had to analyze black holes with two rotations. We didn't find it for just one, but we began to hunt around for other behavior, and this is what you get. These phase transitions have never been seen in any other black holes. And if we believe that there is an underlying quantum theory of gravity that describes black hole degrees of freedom, that theory better well describe this, because it's there. Now, actually, reentrant phase transitions were first seen in nonlinear electrodynamics by Sharmila, David, and me beforehand, but we didn't know what they were then, so we called them zeroth order transitions. And that is, nonlinear electrodynamics is when instead of having Maxwell's theory, you have higher order couplings of the Maxwell field strength to itself. And a textbook one is called the Born-Infeld-Lagrangian, which is given by this. You have a new coupling constant B. If B is large and you expand this, the leading term is Maxwell. But you get multiple powers of the square of the Maxwell field strength. This is fun to play with if you're a classical relativist, because, believe it or not, you can exactly solve these equations in the spherically symmetric case, and this is the answer you get. Here's the spherical symmetric metric. The field strength now looks like this. Notice, if B is large, this goes away, and you get Q over R squared for the field strength, which is what you should get. But if B is finite, then you get this very different behavior where the field strength is not singular at the origin. In fact, that's why these things were invented. If the photon has self-coupling related to B, then in fact the Coulomb potential would not be the Coulomb potential all the way to R equals 0. It would get modified like this, and you'd have a non-singular electromagnetic field. Unfortunately, we don't have evidence directly the photon classically self-couples. But here is the metric function. It's given by this complicated hypergeometric function of Q over R squared, but it is solvable. And you find, here's the field strength versus R, which I say, instead of going up to infinity, it actually goes to a finite value, depending on B. And the metric function, you have two types of black holes. If I forgot about this thing, or rather if I expanded in powers of B, I would get the Reissner-Nordstrom function, which has, as metric function versus R, it grows like R squared. It has a 0 for the outer horizon, but then it goes back up to have an inner horizon. However, if B is large enough, I only get one horizon. And then I have a marginal case that's the boundary between the two. So I have two kinds of black holes. One class looks like Reissner-Nordstrom that has an outer or inner horizon that goes extremal and a naked singularity. The other has only one horizon, the so-called S type. So here are the variables, thermodynamic variables. So let's see if this is like a Vanderwaal's thing or not. This is satisfied.
What is VDV?
What is which?
VDV.
I'm going to tell you that in a minute. There is an extra term that came about that was needed to be satisfied. B is the coupling constant, which we found we needed to include in order to satisfy the Smar relation, and capital B is the derivative of M with respect to little b. I didn't put the mass in here. The mass is complicated. The mass turned out to be a function of little b, and if you vary it with respect to...
M is equal to PS.
Yeah, Yeah, but I don't have it explicitly in terms of R plus and so on. But M is a function of R plus Q and little b. Capital B is dm dB, dm dB. So we found that you got, when B is larger than this 1 over 2Q, you got a standard swallowtail Vanderwaals picture. But for B in this range, we got these double swallowtails giving this, well, not double swallowtails, we got the small part folding, instead of going off to the left, it folds back and goes off to the right. And we had these 0th order phase transitions. You come up here, hit the swallowtail, and then you have to jump again. And then when B is in this range here, we had 2 critical points, only one of which was a minimum, and that came from this complicated Gibbs free energy structure, which is explicitly known, but I don't have any good intuition for hypergeometric things, so you had to plot them. This 0th order phase transition, we did find this diagram, and we didn't know it was reentrant then. When we looked at the rotating case, we found the same thing, and that's when I dug in the literature. I said, if this is, you know, if this is there twice, either black holes are really weird or this exists someplace else. And it actually was a biophysicist in our department named Beta and Hall. So I think I've seen this before. Look at this book. And it was there. So that's the enlargement of this pressure volume diagram, which I've already showed you, but we first saw this in nonlinear electrodynamics as a discontinuity in the Gibbs free energy. I'm running out of time, so I'll just show you that the critical ratio at criticality is 3/8, but with this correction as a function of B that you can expand. Which again shows you that criticality is very different depending on which species of black hole you are looking at. So there is a Maxwellian branch. If I look at this critical ratio as a function of the parameter B, the Maxwellian branch is here and asymptotes to 3/8. But once I hit this point here, I've got the other, we called it the Born-Infeld branch, but this is for this other class of black holes that have just one horizon. However, these don't change. Even though all this other structure is different, this is still a mean field theory type of black hole. So what about this parameter capital B? Well, capital B, when you compute it, is given by this explicit function here in terms of Q little b and R plus. And it is to little b what volume is to pressure, what angular velocity is to angular momentum, what temperature is to entropy. It is the conjugate variable to little b. So we called it the vacuum polarization parameter. Born-Infeld electrodynamics has that classical vacuum polarization, unlike Maxwell, which does not. In a vacuum, there's no vacuum polarization. In quantum electrodynamics, there is. Inside a substance, you can have magnetic permeability, but basically in empty space, you don't have it. But when you have nonlinearity, you do. So you can plot B versus little b, and you get all these different cases, depending on the values of the other parameters. And you can plot Gibbs versus little b, and you get, again, this very complicated behavior. This was a harbinger to a paper by Castor, Ray, and Trashin, where they pointed out that basically, and this is a bit universal to get to your question, any theory which has dimensionful parameters will have a thermodynamics associated. And this is going to come out in Lovelock gravity, as we will see next time. That in fact, variable lambda is not unusual. It actually should be regarded as common. And if you carry through these arguments I mentioned before, you find that dimensionful parameters in an action have thermodynamic behavior. There are thermodynamic variables and conjugate variables to those. And these guys did it for Lovelock and full generality. So next time, I'm done today, next time we're going to see more exotic things. You could have multiple reentrant phase transitions, I'm going to show you something called a thermodynamic singularity. That I don't know exists outside of black holes. I'm going to show you isolated critical points, critical behavior that is not mean field. I'm going to show you black holes that are superentropic, black holes that are like superfluids, and later on we'll get to heat engines. And that's in a number of these papers here. So thanks again for your patience for this session. 8 minutes early, so there's a good question. Or food.